Hi, my name is Chloe McJunkin, and I decided to use the college student data, and out of everything, I decided to do the age and the amount of siblings. So here is the age and siblings again. It was a sample of it of 30. And here is my histogram. I had 5 classes with a class width of 4. It is not bell-shaped. It is skewed to the right because it's all the way, the largest one is on the left. And it is single modal, also called unimodal. The median would be my most relevant measure of center. And the mean is 20.733, the mode is 20, the median is 20, the mid-range is 26, the range is 16, the variance is 9.7, the standard deviation is 3.1, the POV is 14.983, the minimum for the values of the age is 18, the maximum is 34. The first quartile is 19, the second quartile, or the median, is 20, and the third quartile is 21.75. The interquartile range is 2.75. I have a lower fence of 14.9, an upper fence of 25.9, and then I have one outlier that is at 34. The mode and the median are both very close to the mean. This is the z-score. The z-score is very close to the mean because it's only around 0.24 standard deviations below the mean. And this goes to, I can't say it, Chebyshev's rule. And his rule states that at most 25% of a given data set can be beyond 2 standard deviations for any distribution. So what I did is I took the ages, I calculated the mean, and then the standard deviation, and then I found the z-scores. And I like this because you can just drag it down and it'll plug in for all the values. Out of these z-scores, there is only one that goes beyond 2 standard deviations. So one number of points beyond 2 standard deviations. So that percentage out of all 30 of these is 3.33. And because 3.33 is less than 25, it does indeed fit Chebyshev's, or however you say his name, rule. So it is accurate. Proportion. So the given question is, using your sample, estimate the percentage of this population that are an only child using a 90% confidence interval. My answer that I found was, using a 90% confidence interval, I estimate that between 52.51% and 80.82% of the population are an only child. So that is the population perimeter, being an only child. My bounds of interval are between 52.51% and 80.82%. And to find those, you multiply these by 100. So, in other words, if we repeated the study many times, 90% of the confidence intervals we calculate would contain the true percentage of the population who are an only child, which we estimated to be between, my goodness, my screen's acting up, 52.51 and 80.82. So this interval gives us a likely range for the population percentage based on our sample data. Here is the hypothesis test for the mean. The given question was, using your sample, test the claim that the mean age for this population is more than 19 years. I decided to keep the significance level, which is A, at 0.05. For the hypothesis testing, this is the null hypothesis mean, which is equal to 21.4667. So the average value for the population is this. This is just the default assumption that we started with. This is the alternative hypothesis mean, which is greater than 21.4667. And this is the thing that we're testing for, that we're trying to figure out. So we're trying to figure out if there's enough evidence that the mean is higher. My p-value is 0.01416, and my test statistic, also called just t sometimes, is 2.523. You can say that there is sufficient evidence that the mean age for this population is more than 19 years, because the p-value, going back down, which is 0.014, is less than the significance level A of 0.05. So we get to reject this and conclude that there is a significant evidence that the population mean is greater than 21.4667. This is the correlation. My questions were: determine if a significant linear correlation exists, which is testing at 0.05, between the age of a member of this population and the number of siblings a person has. So we're trying to decide if the age of somebody directly correlates to the amount of siblings that they have. And then the corresponding question was, use the results of the correlation test to determine the age of a person if they have 8 siblings. That's where you use your linear regression equation, which are, you have to find your slope and your intercept, which are also B and A. So your regression equation is age equals A plus B multiplied by the given value, which now it's 8, because we're trying to find 8 siblings. So we found that the intercept is 4.3597 plus the slope, which is negative 0.0804. Doing all the math, the age is equal to 3.7. However, because the correlation is not significant, so it's a weak negative correlation, because R is equal to negative 0.2263, it's not reliable. It's not a significant statistic. I have a sample size of 30. I found a t-value of negative 1.2296 and a critical value, which was at 0.05, of 2.0484. Here's that scatter plot. And while this looks like there is a direct correlation, there's, again, not enough evidence. This prediction is most reliable for ages 18 to 24, because most of the data points fall within that range. There are only a few select ages outside of the range, which includes 30, 29, and 44, which is right there. So predictions for those ages may be less accurate, and they are at risk of extrapolation. Again, we only used 30 because taking that as a sample. And that's it.